Welcome to qnawire.
We are asked to find the photon frequency that is required to excite the ESR transition in a magnetic field of a value B equal to 0.35 Tesla. So to do this, we're going to consider the fact that the spin of the electron in sub s is plus or minus 1/2, that the spin state S here is for the spin angular momentum is equal to m sub s times h bar, where h bar is Planck's constant divided by 2 pi. The possible values again of m sub s are plus or minus 1/2. And the energy, delta E, is equal to the charge of the electron divided by the mass times the dot product of the change in the spin state from the flip times dotted with the magnetic field B. But of course, the change in energy is also equal to Planck's constant times the frequency, so we can use this to find the frequency. So delta S is the change in state, where we're going from the spin up state, spin positive state. We're going to subtract from that down state or spin negative state. We plug in equals m sub s equals positive 1/2 for the positive state and minus 1/2 for the negative state. So this comes out to just equal h bar, because it ends up being 1/2 h bar plus 1/2 h bar, which is just equal to h bar. And the dot product between delta S and B is just going to be S times B, since they're at 90 degrees with one another. So then, or excuse me, perpendicular with one another, parallel. So delta E is going to be equal to E by M, where M is the mass of the electron, E is the charge, times H times the magnetic field B. This is equal to H times F. Again, H bar is Planck's constant divided by 2 pi. So we can solve for the frequency, and we find that the frequency F is going to be equal. So I'm going to replace H bar with Planck's constant divided by 2 pi. So the Planck's constants are going to cancel, and you're going to end up E divided by 2 pi m times the magnetic field B is equal to the frequency. Putting these values in, we get a value for the frequency of 9.79 times 10 to the 9 hertz. So we can box this as the solution to our question.